Barnabé is leading the robust incentives group at the Ethereum Foundation. And he's kind of like one of my go-to sources for understanding the Ethereum ecosystem, especially for things that concern economics, and in particular, the interaction of economics and CS, because he's very much a part of the EC community, but also really ingrained in the Ethereum community as well. So he's going to speak to us today about rollups and the economic questions there, and I will let him get started.
Yes, thank you, Matt, and thank you for the invitation. I'll start by sharing the screen. Which you should all be seeing now. Yeah, so today I want to talk a bit about this idea of scaling Ethereum, and I want to specifically focus on rollups, which are really the main way that the community is looking at for scaling. Yeah, without further ado, why should we scale? Like, where does this question come from? I think to understand that, we have to come back to what Ethereum is in the first place. That's how I would define it. I think there's many definitions, but to me, Ethereum is an attempt at getting this global distributed computer that's able to run programs that are committed to by really anyone. So the platform is fully open and is maintained under consensus with a set of validators, which is open and dynamic. So anyone can join the set of protocol maintainers or operators. But Ethereum, like any other computer, it has finite capacity. So it just cannot run everything that we send to it. And if we have finite capacity, that means we have scarcity in the system. And if we have scarcity, it means that we are going to induce fees. So we're going to have to decide what is the best allocation of the Ethereum resources as a computer. So these fees, of course, they lower the user welfare because users have to pay more to access the system, and they shut out many more users or use cases or even developers who would want to develop on this computer. And so the idea of scaling is to allow more of these use cases, more of these users to use Ethereum as a global distributed computer. Another thing I want to say before diving into the theory and let's say nitty-gritty of how rollups work is that this transition to the rollup world of Ethereum is already happening. So this is a plot I took from L2Bit, which shows the blue line that you see at the bottom, which kind of flat lines. This is the throughput of the Ethereum base layer, so what we know as the Ethereum chain today. And you can note that it's not very high. So it's around 10 transactions per second. This TPS metric is not a very good one, but I think it works in that case. And what you see in red, the curve that's above, the total throughput of all the rollups that are settling on Ethereum. And what you're seeing with the scaling factor is that these set of rollups today execute almost 5 times as many transactions as are executed on the Ethereum base layer. And so when we think about scaling Ethereum, what we really mean is that we essentially want the scaling factor to be as large as possible, because we consider the transactions that are executed on the rollups, so on this red curve, be part of the transactions that are executed in this Ethereum global distributed computer. So today, Ethereum for me is not just the base layer, but it's really the base layer plus all of these rollups that exist and process user transactions. And so to get to that point, I want to take a bit of an historical view of how Ethereum got to this point of thinking of itself as rollup centric and deciding that rollups would be a way forward for Ethereum to scale. So around 2019, the researchers and the developers of Ethereum started talking about scattered collection of upgrades and giving it a name, which was Ethereum 2.0. It was a bit infamous because we tried to deprecate that name, but it really stuck. But what it really tried to convey is that there was this mutation of Ethereum that we were trying to really changed the way that it works in very fundamental ways. And two of the, I would say, flagship upgrades that Ethereum 2.0 covered are the merge and execution sharding. So the merge was this idea that we would move from the proof of work consensus mechanism to proof of stake. So that was really like changing the way that the operators of the system are governed and maintain the consensus. And then the second upgrade was execution sharding. So scaling the network by essentially having many, many more chains running in parallel that could process more of these user transactions. So we got to the merge. That happened last year, September 15th. We definitely moved away from proof of work and into proof of stake, but execution sharding never really saw the light of day. It got kind of replaced with this idea of rollups. And so I want to kind of explain how we got from one to the other. Before that, some concepts that will be useful. So a little bit about how Ethereum works under proof of stake. So Ethereum is like a chain, which you can see depicted at the bottom. And the chain essentially recruits a set of entities which are known as validators. And validators can be anyone who owns at least 32 ETH. So you put this 32 ETH at stake, and then you declare yourself available to perform validation duties. And if you do a good job, you're rewarded by getting some kind of reward on top of the stake that you put in the system. If you don't do a good job, you get penalized. So you have something at stake, which incentivizes you to maintain the network properly. So the role of these validators is to produce new blocks, vote on what's the current head of the chain, finalize blocks, the whole thing that has to do with the consensus. And so the idea of execution sharding was that if we have this set of validator, which is pretty large, we can copy paste the one chain that we have today into, for instance, 64 was the number that was thrown around at the time. We could copy paste the chain into 64 parallel chains and split the validator set, so randomly sample validators and shuffle them once in a while and get each set to validate just one of these 64 chains. And then we would have some kind of logic that would allow some sort of message passing between the chains, and the whole system would be secured by this validator set of Ethereum. This turned out to be actually pretty hard to conceptualize and to get it right. One of the reasons why it's hard is it's a very top-down way of organizing the way that Ethereum scales. Like we say, we have this very opinionated view that this has to be 64 is the number, potentially an opinionated view of what kind of virtual machines are running on these chains. So there was a lot of decisions to make. The message passing was also a bit tricky. And along the way, as this idea of execution sharding was progressing, this idea of Rollup was coming to the scene and really starting to convince that people that, okay, this is another way that we can do it, which is not top-down, which is not something that the protocol designers even have to be concerned with, but that the market sort of figures out that is secure and that brings this scaling to Ethereum. And so then we started thinking, okay, maybe we don't need to go into this very hard execution sharding path, which potentially is not the right solution, and we can just let the market experiment with these rollups instead. And so what do we mean here by secure sharding or secure scaling? So what I said earlier was that execution sharding was secure because you have all these validators that are securing each shard. So the idea of secure is that if you want to break the scaling solution, you have to break Ethereum. So in the case of execution sharding, if you want to break or make a safety fault on one of the shards, you have to break the validator set of Ethereum, which you're sampling from to secure these shards. If you're doing that with Rollups, it's a bit more complicated, but we'll get to that. And so the naive idea to scale is to say, well, Ethereum is a computer. If we can't have enough space on Ethereum to run the programs, why don't we run these programs outside of Ethereum and just report the computation back to Ethereum? But the problem with that is that Ethereum must be convinced that when the program was run outside of its domain, that it was indeed run honestly and correctly. So it's not enough to just report the computation. we need, as Ethereum, to understand that the computation was indeed correct. But if Ethereum validators and if Ethereum full nodes have to re-execute the program, then there's just no scale. So is there a magic bullet here? So can we get to a point where we can do this computation off-chain and have the security guarantees of you have to break Ethereum to break the scaling solution? Is there a magic bullet? And I'm going to argue in the next few slides that rollups constitute essentially such a magic bullet, but it needs a little bit of construction before. So let me just start with an example of what could go wrong and what are the cases that we're trying to build our way around. I'm going to take here the example of tokens. So tokens are just simple programs. They're registries that essentially tally up what is the balance in tokens of every user of that token. And the application I'm focusing on is just payments. So what you want to do is have on this domain that I call of Ethereum, essentially payment channels. So that the users that are on of Ethereum can just send each other tokens back and forth. And what I want to do is eventually, I want to be able to settle on Ethereum the balances of the users that have exchanged these tokens with one another in this other domain of Ethereum. And so an example of what could go wrong is the following. So Bob could lock 3 tokens on Ethereum and transfer them to this domain so that he has access to these tokens on of Ethereum and is able to transfer them to users over there. Let's say in the second step that Bob sends 1 token to Alice, and that in the third step, Bob makes the claim to Ethereum that he wants to withdraw 3 tokens. So we know that this shouldn't be possible because Bob started with 3 tokens, sent 1 to Alice, so his balance on of Ethereum is now only 2 tokens. But if he claims to Ethereum that he indeed is the owner of 3 tokens on of Ethereum, how can Ethereum know that this is true? And for that matter, how can Ethereum know that any claim made by someone who is living on this of Ethereum domain is true? So again, we don't want to have to re-execute the whole sequence of transfers that happened to verify what the balance of Bob really is, because otherwise we just don't have any scale. So how can we figure out a way to convince Ethereum that this withdrawal is correct without having to re-execute everything? So the first step in the construction is that Ethereum needs data. So it doesn't need to re-execute the transactions that happened on this domain of Ethereum, but it needs the record of the transactions that happened there. So the data that was executed, and the data is really just a sequence of transactions written out as just raw bytes. The data needs to be published on Ethereum. So every full node, every validator that constitutes Ethereum needs at some point to be able to access this data. So this guarantee, we call it data availability or data publication. And the step we're trying to make is that we want to ensure that this data is common knowledge to all the participants of the Ethereum network. Confusion that often comes when we're discussing these concepts is that the data needs to be stored indefinitely. Actually, this is not the case. So the guarantee that we need at this point is really this common knowledge. But once we are guaranteed that the whole Ethereum network has learned about this data at least once, we don't actually need to keep this data around. So that gives us also a little bit of scaling in that the nodes of Ethereum don't need to keep the data as a record permanently. So the first step is data. Ethereum needs to be aware of the record of what has been computed. And now the second step is Ethereum needs to be convinced that the way this data was executed, the way that the transactions of the data was executed is correct. And for that, Ethereum needs a proof. So it needs something that tells it that the data was executed correctly and that it leads to the current state of the rollup that the user is trying to bring back to Ethereum. For that, there's actually 2 ways, and there's really like these 2 types of rollups that are deployed today. The first type of rollup is known as optimistic. And in fact, in optimistic rollup, you don't really have a proof that the data and that the transactions were executed correctly. You rely on an economic mechanism where somebody puts at stake some amount of money and says, you know what, I will tell you that the thing I'm claiming is correct. And if you can prove me wrong, you can slash me for the money that I put at stake. And so optimistic rollups scale this way. So you don't have a proof, you don't have to convince Ethereum, but if anyone raises a flag and says, wait a minute, I don't think that this claim is correct, a game starts where there's a challenger and a prover or an asserter who are trying to get to the root of a disagreement. So that's one way. The other way that Ethereum can be convinced is with just raw cryptography. So there's new technology, which are called succinct proofs, which allows a prover to essentially take the data that was published on the rollup and claim that given this data and given the assertion that is made about the state of the rollup after the execution of this data, that the data was executed correctly. It's kind of magic. It's as if I told you that the program was correct and you don't have to run it to believe me. The cryptographic proof tells you that the execution was done correctly. So these are known as snarks or starks, and the rollups that use this kind of approach are known as validity rollups or sometimes ZK rollups. Okay, so this is really almost all we need to have rollups that are as secure as Ethereum, in the sense that Ethereum is able to decide by itself that what happened on the rollup was correctly computed. But I want to make the distinction here between, let's say, two types of why we need the data. So it is a bit of a different role for each type of rollup. So for optimistic rollups, we need the data so that we can dispute the assertions that are made by the person who's trying to make a withdrawal. So the data needs to be public so that anybody can challenge the execution. For validity rollups, I can prove to you that I advanced the state of the rollup correctly without telling you what happened there. I can say, given a sequence of transactions that you don't know about, I can prove to you that I did the math correctly and these are the balances at the end. But if I don't give you the data that led to this new state, nobody other than me can advance the state of the rollup. So I can prove to you the correctness, but I can't tell you what's in there. So we need the data to be public so that in case a single operator on the rollup is advancing the state, anybody can replace them if the operator goes down or if the operator becomes malicious. So the kind of attack that I can do is say, since nobody knows the data and I'm the only one who can advance the state, I will try to extort you so that if you want to withdraw from the rollup, you will have to pay me for me to get you the correct state. And so that's bad. These types of attack, it really has to do with liveness. So what I claim here is that with the proofs and the data, the safety of the rollup is guaranteed at the same level as the safety of Ethereum. But we need a little bit more to get the rollups to be as live as Ethereum is, meaning the rollup can keep going as long as Ethereum keeps going.
Barnabé, there's a quick question. Just clarifying, when you discuss the validity rollups, is for people in the audience who don't have quite the same cryptography background, could you share a little bit about what are the kinds of statements that could ever be proved efficiently by snarks, or what are the kinds of statements that could be proved efficiently now? Or do you have maybe just some commentary so people have a sense of where that's at right now and where that might possibly be in the future?
Yes, yeah, this is a good question. So efficiently is another statement because computing these proofs is actually pretty difficult, but it's possible. So historically, snarks were only available at the beginning for simple types of programs. So for instance, transfers between users. So given a sequence of transactions that were transferring money from one user to the other, you could compute a proof of validity for the resulting state of the balances after a sequence of transfers. Since then, there's been a lot of effort and a lot of money poured into making the snarks more general purpose, to the point that now you have these rollups that claim to be EVM equivalent. So whatever computation you can run on Ethereum, you can prove it with a snark, which means that any smart contract that is published on Ethereum can be proven with such a snark. So yeah, that allows you to essentially run universal computation on the rollup and obtain proofs that the computation was done correctly on the rollup itself.
Thanks.
Yeah, good question. Right. So I just want to end with that on the technicalities of rollup constructions is how do we ensure that liveness is recovered and that we don't get stuck on a rollup that just isn't processing any new kind of transaction. This will also be important to some extent when we dive into the economics. And so the first strategy that rollups are considering is the idea of decentralizing the role of the rollup operator. So I didn't really give details on who exactly runs the transaction on the rollup. I'll be a bit more precise about this in the next sections. But one general idea that you can have is you don't want a single person to be in charge of processing the rollup transaction. Like you want to be able to rotate the operators so that if one of them is doing a bad job, another one can replace them and keep the rollup essentially active. A second strategy is that even if you have these decentralized sequencers, you don't want to find yourself in a situation where none of them will allow your transaction to be included. And so if you want the censorship resistance properties of the rollup to be as good as the censorship resistance properties of Ethereum, you can think about this force inclusion feature, which is that if you want to do a transaction on the rollup, you get it included on Ethereum as data, and the rollup has to execute this transaction to keep moving. So even if the sequencers are malicious, if they want to keep the rollup moving ahead, they have to include this transaction in their transcript, essentially. And so by that, with that feature, the rollup becomes as censorship resistant as Ethereum is. And so with these two things, we should essentially get the same liveness on the rollup as we have on Ethereum. Okay, so that was quite a bit of information already, but I really wanted to explain that this construction just isn't pulled out of thin air and works and has the properties that we care about. And just like as a brief recap of what we've seen, so this idea that rollups essentially move the execution of Ethereum and that you have these bridge contracts that allow assets to be moved from one domain to the other. So if you have tokens on Ethereum, you can move them on the rollup, do things with them on the rollup, and later on withdraw them. Then the idea that rollups are secured by Ethereum, so they are as safe and as live as Ethereum is. And finally, I really want to emphasize this idea that apart from these technical requirements that I described earlier, a lot of the mechanics of the rollups are actually left up to them. So they can decide how to design their economics. They can decide how to design many parts of their operations. And this is what I want to focus on in the second part. All right, so first off, I want to focus on what happens from the point of view of a single rollup. And later on, I'll discuss a bit what happens when you have these networks of rollups. So when you have multiple rollups that are interacting with one another. So the
Actually,
approach
Barnabé, there's a very quick clarification question that just got asked, which was, could you elaborate a little bit on the mechanics for like a force include, like exactly what that would look like?
Okay, so the rollup has a smart contract that is deployed on the layer one, which is, you can think of it as the entry point from Ethereum to the rollup. To force include a transaction, what you would do is you send a transaction to that entry point on Ethereum, and this transaction contains just like the raw bytes, the raw data of the function call that the transaction is trying to make. Now, this entry point will have a record of the transaction you want to do on the rollup. And if the rollup has, as part of its sequencing rule, that okay, if there's something in the inbox of a layer one, I have to process it. Otherwise, any state transition I do isn't valid. Then the rollup will have to include this transaction and execute it as part of its own transcript.
That makes sense. There's it looks like there's also a quick follow-up question, which is so I think maybe last one we'll take on forced inclusion, but would you be concerned with the mechanics you just described that if that's deployed on the rollup, would there be any concerns that like people could abuse this to stop liveness of the main Ethereum by using force include functionality?
So I don't see how it would interfere with the liveness of Ethereum itself. So I think one of the drawbacks of this force include is that you want to transact on the rollup because it's cheap, and you don't want to transact on Ethereum because it's potentially expensive. So if you have to go through Ethereum to get your transaction executed on the rollup, you're going to have to pay a lot of fees. And the fees are kind of what regulates whether Ethereum is live or not from the perspective of its users. So yeah, if a rollup is very important and many users need to use this force include, which again should be a relatively edge case for when the rollup is really in a kind of crisis mode with respect to its sequencers. Yeah, in that case, it could be that the rollup clogs Ethereum so much that any other Ethereum transaction isn't valuable enough to take precedence over the force inclusion. But I think this case, in my opinion, would be a pretty rare, if not, yeah, impossible kind of scenario.
That makes sense. Thank you.
Sure, yeah. Okay, all right. So yeah, the view that I want to adopt when I discuss these now economics of the rollup is there's a lot of moving parts. There's the Ethereum base layer, which has its own internal mechanics. There's the rollup, there's the users. And so what I've tried to describe is really this whole system from a flows and value flows perspective. And so understanding what flows into the system, what flows out, and how do the flows within the system can be designed for maximum either efficiency or optimization of any metric that the rollup cares about. So in the next slides, I'll describe what these flows are. So I'm making here sort of very high-level view of the system as a whole. You can think of it as the users are coming in. They have transactions that they want to make. They are sending these transactions to the rollup box, and that box is like a big operator. And then the rollup has to, as described, send the data of a transaction to the base layer. So that's kind of like this three component system. But there's this big one box that I call a rollup operator. I'm actually hiding a lot of the complexity that happens in them. The operator role for rollups, it can cover many different logical functions which are distinct. So just to discuss a bit what these are, the first one, and potentially one of the most important, is the idea of the sequencer. So the sequencer is the person in the rollup operators who takes in the user transaction and sequences them into blocks or into batches. And so this sequencer is responsible for the ordering of a transaction. And so moving a little further ahead, this matters a lot because the person who's responsible for ordering on blockchains is the one who can extract MEV, but I'll get to that in a few slides. Another type of operator you can have, and this can be bundled with a sequencer role as well, but it can also be thought about differently, is the executor. So the sequencer just gives you a list of transactions, and now the executor is responsible for executing this transaction and telling you that, okay, the state after these transactions are executed is X. And so committing to the state of the rollup that contains a commitment to all the balances of the users after the transactions are executed. Another role is the one of the publisher. So the publisher, once the batches are available and once the executor has made the execution, could be the one who's responsible for posting the data on the base layer. A type of role that we see only in validity rollups is the one of provers. So as I said, making these validity proofs, these snarks, it's actually quite costly in just like real world terms. And so, yeah, so these people are responsible for taking in a batch and outputting a proof that the batch was computed correctly. Then for optimistic rollups, the equivalent here is the challenger who might be listening to the assertions that are made about the computation and raises a challenge if they see that the computation was not performed correctly. So that was a bit of unboxing of what this rollup operator contains. But now I'll focus again on these flows and what flows in and what flows out of that system as a whole. So the first kind of flow and what really is the motive energy of the rollup is the user value. So users want to use rollups because they get some kind of utility out of it. Their transactions have value when they're executed. The value might depend on the state on which they are executed. So you can think of it as, yeah, the user has just a dollar value for getting something done on the rollup. Another kind of inflow, which is quite related to user value, but I want to separate just to make the distinction clear, is the idea that sometimes users do transaction and that triggers extra value in the system. So this extra value, we know it under the name of MEV, maximal extractable value. And you can think of it as externalities that come from some kind of economic activity that's done by the user. And so a typical example is, let's say Alice makes a swap on an exchange that is hosted on the rollup. And after the swap, the prices on two exchanges are unbalanced. So they don't report the same price. And so there is an arbitrage opportunity for someone who can rebalance the two exchanges and align the prices together. And so the person who makes that arbitrage, I call him Bob, would want to, right after the transaction of Alice, place their own transaction and extract this arbitrage, let's say worth $10. So this MEV it's a whole rabbit hole. It's a little out of scope for this talk. But what I can say is that this value, in my opinion, is a bit disputed between the users who create it, the dApps, decentralized applications who serve the user, and the operators of the rollup, who might also want to take a cut on the economic activity that happens on their platform. And so how we decide to assign this value to one or the other, there's many considerations that have to do with efficiency, mechanism design, fairness. So it has to be considered in a much wider frame.
And the quick question is probably from 2 slides ago. I missed it timely, I'm sorry. So there's a question, there's actually 2 questions about just generally what, could you elaborate a little bit more on exactly what needs to go on L1 for the data to be stored there? And could you also comment on whether the raw size of the data that needs to be put there is possibly still a concern?
Yes. So the data that needs to be put there, you can think of it as the record of the function calls of a user transaction. So the user, for instance, says, I want to swap 10 token A against 100 token B. The record of this function call saying, I want to do that, will be posted as data on the base layer. So if you're familiar with how Ethereum works, the function call is known as the call data. And so that data is just posted as sequence of bytes, eventually compressed into the base layer. So that's one thing. In the case of validity rollups, you also need to post the proof as data, so validity proof on the base layer. And you might also need to put an assertion to the state of the rollup. So you can compute the hash of the current state of all the balances and post that on the layer 1. And so then the game is the layer 1 has to figure out whether, given the data of the function call transcript posted to it, and given the hash of the state that was committed to on the L1, whether the two match with one another. So these are the two parts that you need to post on the base layer. Okay, yeah. So two system inflows, the user value and the MEV. And now one kind of system outflow. So how might the system as a whole, let's say, lose money? The user value might just be degraded by passing time. So the longer they sit unserved, the more they have to experience congestion on the rollup because maybe the capacity is reached. The more the user value just degrades and disappears. So I think this one is fairly uncontroversial. Another kind of system outflow that the system as a whole needs to account for is that the operators of the rollup, they expend real world resources, which are just costly in US dollar terms. For instance, if I'm running my validity prover on AWS, I need to pay the cost of the cloud resources that I'm using. And this is just an invoice that lives in the real world and not Ethereum. So one way or another, we have to find a way to get these operators enough money so that they can process the transactions of the rollup. And then another way that value leaves the system is the base layer costs. So when we post the data on the base layer, we have to pay something for the base layer to carry the data for us. The way this is done today is with the fee market known as EIP 1559, where anything that's paid to the base layer is essentially split in two. So you have the minimum protocol fee that's known as base fee, and that one is burnt. And you have then tips that are given to the L1 block producer. And so for your rollup to keep being secured by Ethereum, it needs to expend these two costs. Another interesting item in this categorization of inflows and outflows is the idea of issuance. So it's a pattern that we've seen many rollups do. And the pattern is to introduce a token, so a new token, because Ethereum is programmable and because these are, again, universal computation machine, the tokens can be programmed to be pretty much anything. So some of them can look like equity when you think of a rollup as a private company, for instance. Some of them are useful to vote on decisions that are made by the rollup. And some of them can be utility tokens. So you might require the gas or the resources used by your rollup to be paid in the native token issued by the rollup. So I think of the token as almost like a battery. So if the price of a token goes up, it inflows more value into the system. So if your token price goes up, it's maybe more money that you can pay to your operators so that they offset their real world costs. But if the value goes down, that can also be an outflow from the system. And so this idea of how to design the token so that the token helps the rollup achieve its goal, to me is a big open question. And it's something that we're seeing people iterate over. And I think there's a lot of very interesting natural experiments that are being played out in this field. And so, yeah, synthesizing, this is essentially the map of the costs and inflows that we have for this system. And so then the game is to just draw arrows and connect these boxes together so that we ensure that the operators can pay their costs, that the L1 receives the cost necessary to publish the data, and that user value is maximized. This is one possible way that we could connect. So I'm taking in some examples. Some rollups have airdropped their tokens to the user so that they promulgate more utilization. I draw this box here, which we find also to be pretty common public goods. So some rollups are essentially incorporated as DAOs, and so they have a treasury that they can use to fund public goods or to fund projects related to the rollup. And the way that they are making money for this treasury is either taking a congestion fee or taking a surplus from the rollup operations. So there are really many ways to design mechanisms that allocate the fees and the costs to the different parties making up that system. And to me, it feels a lot like sometimes just operations research and trying to understand how to design the system optimally so that things keep chugging along and everyone is happy. Now I want to give like some ideas of what can a individual rollup optimize for. So the first one is the idea of batch data scheduling. So we know that the rollup needs to post data on the layer one regularly. And actually Ethereum is now building in a new upgrade called EIP 4844 that provides a special facility for rollups to post their data on L1. So today, the data is simply posted using the old system, so just as a regular transaction on Ethereum. But what we're now trying to offer, you can think of it as a container. So the Ethereum protocol offers these containers for rollups to park their data in there. So as I said, this data doesn't need to be kept around forever. So we get a little bit of scaling here. The blobs, which is batches of data posted by the rollups, can just be known to everyone and then discarded after a few weeks. One interesting question that popped up is when should the rollup post that data? So there's a fixed overhead when you pay for one of these containers, one of these blobs. So you want to wait until you get enough data to fill your container. But at the same time, users also care that the data is posted relatively quickly on the base layer because this allows the rollup to provide these security guarantees. So you also don't want to wait too long. And there's been some interesting research done by off-chain labs on figuring out these efficient strategies for posting the data. Another kind of problem that pops up in many places for the rollup operators is the deferred payment problem. The idea here is that we want to charge the user at transaction time. So when the user comes in with their transaction, we want to charge them something and then process the transaction later on. But there are many costs for the rollups that are incurred in the future. So for instance, a bunch of users come in, pay you something, but at the end of the day, you have to post the batch to the Ethereum layer one. And you don't actually know necessarily what the price of posting the batch will be at the time that you are charging the users. The price on Ethereum, governed by EIP 1559, has this dynamic fee, the base fee, which is unpredictable and which can vary pretty drastically from 1 hour to the next. And so there's a big question for rollups, which is how should they charge the user and how should they manage the price risk? So one avenue that we've been exploring is the idea of derivatives based on the L1 base fee that would allow the rollup operators to hedge the price movements on the layer one so that they can charge the user correctly when the user comes into the system. A third type of problem that looks a bit like operations research is we require to get these proofs for the validity rollups, but these proofs are very expensive and they require fairly specialized computation to be done efficiently. There's many ways that we can organize the provision of these proofs. There are just properties of the cryptography, such as recursive proofs that allow us to split the work in intelligent ways. But remains the question of how should the rollup go and find suppliers for making these proofs? Or how should the rollup reward and incentivize provers to make these proofs timely first, but also efficiently, so without overpaying for making these proofs. We've been thinking about it with some protocol fellows. There's a repository here with a lot of links related to that problem. And I also like a lot this video from Togrul from Scroll, talking about how to find these provers and how to align them into that system of operators. Yeah, so that was for the single rollup. And perhaps I pause here in case Matt has a question.
No questions right now. There are definitely a bunch for after the talk.
Okay, great. So we are batching them and posting them
Yes.
at the end.
Oh yeah,
Perfect.
there's plenty of stuff. Yeah, but I tried to take only the quick clarification ones live.
Cool, cool. All right. So this was kind of a study of how a single rollup wants to organize its own operation and the sorts of problems that this single rollup faces. When we consider that, well, rollups are this market-driven solution, anyone can spin up a rollup, we will notice that we're starting to see a topology emerge. So why do rollups get created and how do they connect to the layer one and how do they connect to one another? So unlike this execution sharding plan, the rollups are really just driven by market forces. So if somebody thinks that they can do a better job at operating a rollup than one of them, they are going to want to start their own, and they can just spin them up permissionlessly by just deploying a contract on L1. So the rollups, they root on the base layer, but they also talk to one another via bridges that can come in many different shapes and sizes. And so this network of rollups and these networks of communication and message passing is really dynamic and expanding. And so what I want to get into with that section is what are the forces that drive these rollups and what is the emergent topology and the kind of revenue sharing or services that the rollups come into to share these costs. And so two particular places that I want to look into is the idea of liquidity first, which is very important to understand why things organize the way they do, and costs second. So starting with liquidity, what's probably most important for a rollup is to have assets under its control. So the more assets are on the rollup, the more useful the rollup becomes to the user, because if there's more assets, if there's more activity there, the rollup can move their own assets and participate in that internal economy of the rollup. And so the assets can move with these bridges, but frictions still exist and costs. And so the domains here are yeah, I think of assets moving between Ethereum base layer to the rollups, between rollups themselves, and even with chains that are outside of Ethereum. Like this is very common to, for instance, have a virtual representation of Bitcoin on Ethereum, or assets moving to Cosmos. All of these use cases exist. And what underpins these connections is bridges. So bridges come in many shapes, but I'm really focusing on two here. The first one is market-driven bridges, which are essentially two counterparties on each side, so on domain A and domain B, just hosting or parking assets and allowing users on each domain to get some of these assets. For instance, if I want to get some BTC on Ethereum, somebody will park some BTC on BTC and provide me with a virtual representation of BTC on Ethereum. And so these counterparties, they just look like people taking inventory risk. So they are parking assets, they are trying to seek liquidity on both sides so that the bridge is able to honor these trades. And yeah, liquidity is really what's driving them. Then we have the native bridges, which are the ones that the rollups use to connect securely to Ethereum. But these have their own costs and their own delays. For instance, for optimistic rollups, you technically have to wait for a fairly long amount of time, which is called the challenge period, until you know that the asset has securely moved to the other side. So you give yourself, for instance, a week to allow somebody to come in and challenge the claim that the rollup computation was done correctly. And so the more liquidity we have on one domain, the more useful this domain becomes. And this is really driven by this flow of assets from one domain to the other.
Actually, one of the questions I was initially saving, I think, is very timely for this slide. Can you elaborate maybe just a little bit more? So I think my understanding is that this slide is talking about, say, like some of the wrapped tokens where they're genuinely a different token, and you may or may not be able to exchange it for the true underlying token, depending on security and blah, blah, blah. And then specifically for L2s, is is that more like there's code sitting on the L2 waiting to execute, or are some of the L2s in deployment now also kind of like wrapping tokens? So the specific question that was asked was like, say you have a Uniswap running on L2, is there concerns about like difference in states between those? Is there a sense in which you can like have a token on the L2 Uniswap but not yet on the L1 Uniswap, or like how should people think about that?
Yes. So you should think of Uniswap on chain A and Uniswap on chain B as almost two different markets. And the assets that they have under their the assets that they control in their reserves, they're also separate assets. So what can happen is, for instance, if I have some ETH on Ethereum layer 1 and I transfer it using the native Rollup bridge, what I get on the Rollup is not a wrapped version of ETH. It's actually ETH itself. Like you can prove that this is the same asset. If I use these market-driven bridges, this looks more like the wrapped assets. So somebody on the other side has seen that I've locked up some ETH on domain A, and so they give me some kind of deposit or claim that this ETH exists on domain A, and so I can use a wrapped version of it on domain B. Then it's up to the dApps and to the Rollup kind of do the matching between the native assets and the wrapped assets. And so yeah, it looks a bit like a very complex routing network, which is why I think it's a bit like inventory management, where you have to decide how much of the wrapped assets you're keeping on one side or the other, how much of the native assets you have to bridge to rebalance the inventories on both sides. Yeah, this is actually pretty complex, and I'm abstracting a lot of difficulty here. But yeah, that's a good question.
Yeah, and then in general, I think there's probably 10 to 15 minutes of what I thought were interesting questions, if you want to use that to guide. But definitely have interesting stuff to say. Go as long as you want, and then we'll figure it out with the questions.
Okay. I think I have maybe 5 or 6 more slides. And
yeah,
sounds good. Okay, so I was mentioning liquidity is one thing that drives the overall organization of the rollups with one another. Another one is costs. And so what we are starting to see is rollups almost like teaming up with one another to benefit from cost sharing or revenue sharing agreements. So the first one that I was mentioning earlier, we have this idea of offering containers for the rollups to park their data. But containers, if you can only fill them halfway, this is not very efficient because you're paying for the whole container. And so much like you have for physical containers, you can have these intermediary services that allow the rollups to pack their data together in the same container so that you offset the overhead of paying for the whole container. So this is described in a new paper by Davide from my own team and these two authors from Off-Chain Labs, Ed Felton and Akaki. And they find some subtle result that even in the presence of this new market with the containers, the old market where you're just sending the data, let's say by post, instead of putting it in these containers, that old market may still be competitive in some cases. Yeah, so I won't go into more details here, but just this idea that by teaming up together, rollups might be able to have economies of scale to pay for these containers. So another way that the rollups might want to team up is that MEV knows no bounds. So I said that MEV is triggered whenever a user action just generates positive value somewhere else. This somewhere else doesn't have to be the same domain. So if I do something on rollup A, that might create a way for somebody to get positive value on rollup B. So for instance, I make a trade on an exchange on rollup A. Now, some exchange on rollup B will not have the same price as the exchange on rollup A. So there is an arbitrage opportunity after my trade has been processed on rollup A. And so if you have sequencers on both rollups, which are discoordinated and which are not really sharing these things, the extraction can be very messy. So I need to do the trade on Rollup A, and I need to follow that with a backrun on Rollup B as soon as possible. But without coordinating, I might not be guaranteed that these two things happen atomically. And so the sort of organic solution that came upon is this idea of shared sequencers. So you have this intermediate in the middle that takes in essentially transactions from one rollup and transactions from another rollup and creates blocks that sequence them together so that when something happens on rollup A, you can execute another action on rollup B atomically, and you can extract this cross-domain MEV seamlessly. So that's, I think of it as almost like revenue sharing between the two chains who cooperate with one another for this specific case. So these are two ways that rollups might want to team up with one another, either to offset costs or to extract more revenue. What we're seeing, and I'm taking most of his arguments from Davide's recent posts on the Rollup Economics 2.0, is that this leads to different modes of organizations for the rollups. The first one that he describes is the idea of rollup cooperatives. So in this case, each rollup is its own sort of separate business unit, but because it makes sense for them to use these shared services, so either, for instance, the publication data service or the shared sequencing service, they're just going to route their flow to these shared services. You can think of them as joint purchase agreements. So it's just something that they opt in because it's rational for them to go through that shared service so that they socialize the cost and make it lower overall. And so here there's a lot of open questions on how the revenue or the cost sharing mechanisms should work. And to me, it matters a lot for the adoption of these shared services and generally to lower the cost and increase the welfare that these rollups offer. Another mode of organization that we are seeing emerge quite strongly is the idea of rollup federation. So in this case, you can have multiple rollups that are all organized around the same set of shared services. And generally, these rollups also organize around the same shared token. So to give some example, Optimism, which is a very popular rollup, has introduced the OP token and the OP stack. So the OP stack allows anyone to build a rollup that fits some kind of shared set of standards and that communicates with the same shared services. This is also the case for Arbitrum, which has different rollup constructions that can all live in the same ecosystem and share the same services organized around the RB token. And the same for zkSync, same for Starknet. So it's something that we're seeing reappear more and more often. In this type of organization, the governance around the token, so what the token allows the rollups to do, and the kind of upgrades the token allows them to turn into, is very important here. So how do the rollup manage this federation around the token? Final mode of organization that I want to discuss and with which I'll conclude this talk is the idea of L-trees. We can actually have multiple layers of these rollups. From a technical perspective, it doesn't really make a lot of difference. The data still has to be published at the bottom layer, the L1. But what we can do is have a more general purpose rollup on L2. So a rollup that talks directly to the L1. And on top of that general rollup, we can have L3s, which are rollups purely specialized in doing one thing. So there's a new sort of thesis that's becoming popular in blockchain, which is that when you have a general purpose chain, it's actually pretty difficult to organize its operations to efficiently optimize for a single use case. For instance, Ethereum, because it runs any kind of program, cannot really privilege one type of programs over the other, or isn't really willing to do it in the first place. But if your chain specializes and you say, my chain only does swaps between assets, you can hard code a lot of internal logic in the design of the chain that allows you to, for instance, extract and redistribute the MEV in ways that you couldn't do if your chain was more general purpose. And so what we're seeing is that rollups are starting to allow these custom purpose L3s to be built and rooted on their more general rollups, which exist in the layer 2. And what's very interesting to see is understanding what are the contours of the trade-off, because the more domains you have, the more cost you have to bridge messages and bridge assets from one to the other. And so what are the kind of use cases that make sense? This is very much a question that is not solved in my mind. Yeah, this was it. It was a very brief overview, and I mostly wanted to tell you that these problems exist, and I think they're interesting. But I'll take some questions now. Thank you.
Awesome, thank you. So I am just going to go through the questions chronologically, so it may be a little bit of jumping around. So the first one, I think, is trying to get at generally, can you comment, or do you have any sense of how much cost savings is really happening due to rollups? So the way the question was asked was, for optimistic rollups, you got to lock up a bunch of capital for the optimistic rollup to plausibly work anyway. That's a real cost. Is there any way to reason about what that cost is compared to the cost of just putting it on L1 directly?
I see. So in this specific case, users themselves don't have to lock up any capital on the optimistic rollups to get their transaction processed by the rollup. The person who has to lock up stake is the rollup operator. So in the case of the optimistic rollups, I think you would want the executor to lock up stake, because they're the ones who make a claim about the state of a rollup after the transactions have been executed. So a single party puts some stake, and the users don't have to pay anything extra. In fact, because the optimistic rollup doesn't have to compute the validity proof, which again is something that's pretty expensive in just real world dollar terms, it's been argued that optimistic rollups are potentially cheaper than validity rollups, because the only cost that is incurred for the operators is the cost of running the full nodes to follow the state of the chain, and the cost of capital when you're locking that stake up. But other than that, it's a pretty light configuration.
Thank you. So the next question, so I think I remember one of your earlier slides, it sounded like you were mentioning kind of the dream rollup would be that it just inherits all the security of Ethereum or something like that. And that I think the question being asked is maybe phrased as like, how close are we to that right now? Is that realistic? And the specific questions were things like, what about how do you feel about having a centralized rollup operator or a centralized sequencer? And what does that mean in terms of regulation, in terms of, censorship and stuff like that?
Yeah, it's a very interesting question, and also something that we're seeing like more and more variety in the wild. So this website that I was mentioning at the beginning, L2Bit, actually has for each rollup dissects the claim that they are making with respect to this ideal rollup ID. So the ideal rollup, for instance, has a decentralized sequencer, this forced inclusion, permissionless data posting, etc. Not all rollups are there. In fact, most rollups are not there. A lot of rollups have what people call the training wheels. So Vitalik wrote this post to say that, okay, there are several stages of decentralization that the rollups can go through. And on L2Bit, the stages of the rollup are also denoted. And you'll find that most of the rollups are not at the final form yet. And there's many reasons for that. So some of them have fraud proofs that are working. Some of them don't have that yet. Some of the provers for the validity rollups still are centralized. So there's no open competition for provers. But most rollups are thinking about these questions. If you go on their various research forums or platforms where they talk about this, these questions are very much being addressed. A little slower than maybe we would like, but still being addressed. And I do think that a lot of the reason why they don't have any easy answer is that a lot of the arguments at the end of the day are just economics. Like how do you design this mechanism to ensure that all the incentives are aligned between these different parties?
Yeah. And then the next question chronologically was how does the volatility of the base layer gas fees, does that impact the frequency at which rollup data is published to the base layer? Like, are rollups being strategic about that? Are rollups promising to publish at regular intervals, or how does that work?
Yeah, so here rollups are very much free to decide how they do it. So there is no like general recipe. I think I'm aware of at least some of them who do try to manage the price risk in fairly good ways. So they have heuristics that say if the price is like the 99% percentile that we've ever seen, it's probably going to come down at some point. And if it doesn't, we'll just post anyway. So there are rollups that are trying to be smart about this, but mostly based on heuristics. And to my knowledge, none of them are currently using things like derivatives to hedge that price.
And then last one from the audience, and then if there's time, there's questions from me and Fahad too. So for optimistic rollups, there's this problem that I think had been coined the verifier's dilemma, which for the people watching this on Zoom, I think I would largely describe as like, if things are working, then when you verify, you expect to see that everything is correct. And therefore, you would expect to see some kind of like tragedy of the commons, or I don't know if that's the right phrase, but you'd expect to see that sort of like when things are working, it's not worth your effort to verify. But if nobody's verifying, then somebody should try and cheat. And so the question was basically, has anyone solved that? Or I don't know if you can elaborate on like what are the kinds of solution. I don't know how easy it is to do briefly, but like if you could elaborate on just like what's the state of the art with addressing that specific kind of problem.
Yeah, that's a good question as well. So I will mention that there is a paper from the same authors that also discusses that question, which I have not put in this presentation. But so some element of replies that I can give is the first one is we only need one person to raise the flag. So this verifier's dilemma has also been discussed in context where, for instance, all the full nodes or all the validators of the chain need to run the data again to convince themselves of the validity. For instance, Bitcoin at some point, I think, had this wrong state transition because people were just not verifying the data. For the rollup, you have this honest majority assumption. So you only need one person to raise the flag. In the theoretical version of a verifier's dilemma, you're still not guaranteed that there is this one single person. But for rollups, I think we can be somewhat convinced that this will be the case because a lot of people will be running full nodes for reasons other than to challenge these potentially wrong assertions. So if a large enough DApp is running on the rollup, it's pretty clear that they will want to run full nodes that allow them to keep track of the state of their application over time. So yeah, there is an expectation that people will run full nodes for reasons other than to check the proof, but checking for wrong state transition is a marginal cost on top of running the full node. So we are pretty confident that someone will have a full node running and that this full node will be also checking for the correctness when it needs to. You're muted.
Sorry. Yep. Rookie mistake. So there's one last question from the audience quickly, which is just, is there any way to calculate the L1 call data cost in advance other than using derivatives? I feel like I have to guess no, just because that could be anything in the future, but I'm so curious to hear if you have like more insight on that.
Yeah, I think this is unfortunately not possible. It's potentially possible to have directionally correct prediction. So if I know that an NFT that's popular is dropping in 10 minutes, I can expect that the price during the drop will be much higher, for instance. But if I was able to predict the gas cost, I would essentially be able to predict any economic activity that would happen on the base layer. So yeah, indeed, it would be impossible to get the correct number. I could get good predictions, perhaps with training some kind of model, looking at seasonality, which exists for these costs, but I can't predict perfectly, for sure.
Yeah. And then there was a comment posted by someone in the audience that if people are interested in reading more about the verified limit from an econ perspective, I don't know if that link will make it into the YouTube video, so I will just read that the title of the paper is On the Security of Optimistic Blockchain Mechanisms. So that's it from the audience questions. I am still going to hang around and ask Barnabé some questions that came up from me and Fahad. I will leave the room open in case other people still want to listen to that, but I'm mindful that it's 12:15, so it will not be considered rude, if anyone leaves now. So the precursor to Fahad's question. So my question is, there's kind of like two plausibly scarce resources on Ethereum, or maybe a lot. One is computation. The other is just the raw data that needs to go into the blocks. And I was trying to ask, my understanding of things from what I've heard is that rollups are primarily concerned with computation being the scarce resource that's being saved, or are there also is the raw data going on the block also being saved somehow in these?
I would say that from the point of view of a rollup, the data publication throughput is the bottleneck that they are concerned with. So they want to be able to post as much data as possible on the L1 for as cheap as possible. And so EIP 4844 is a way of decoupling the market for computation that's offered currently by the L1 from the market for data that the rollups need to access. Yeah, so it's a way of doing multidimensional pricing between data and computation. Yep.
Okay, and so then maybe actually that is relevant for Fahad's question. So when a rollup is posting, say so they post some code on L1 directly, they say this is the code we claim to execute. Are they posting direct references to like Ethereum opcodes, or are they posting references to their own L2 functionality that's more efficient? And then the follow-up question is, if the former, where is the data savings coming from? If the latter, how does Ethereum actually have a permanent reference to what function calls are actually being made?
Okay. Yeah, there's a few questions here, so I'll try to unpack them. So the first one is that the function call doesn't contain all of the opcodes that the function will eventually touch. So the function call is just a trigger to say, I'm calling the function that has this signature with these arguments. This triggers, when it's executed, a sequence of opcodes, which are essentially unit steps of a virtual machine that the computer that is computing it has to process in order. So when I post the function call, I don't have to post also all the sequence of opcodes that had to be executed. So I only have to post the function call. Even if I had to post the sequence of opcodes, I might still have some savings in the sense that I'm only posting it as data, and I don't have to recompute it myself. So again, from this perspective of compute and data being two different resources, it might be possible to post a lot more data than you can actually process. So yeah, data is cheap, bandwidth can be pretty high, but not everybody has like a supercomputer at home that can execute everything very quickly. So yeah, but even then, it's the case that you only need to post the function code. In fact,
Barnabé, can I just ask a clarifying point related to this? Maybe it's just a misconception that I have that'll clarify this. But so I guess, where is the code base associated from the function that's being called? So I guess part of the question here is it, so my impression was that there are, let's say if you say Uniswap on a layer 2, it's different than the sort of Uniswap code base on the layer 1. So there's like new code that's deployed. Now we're using the term Uniswap for both, but in principle, I could deploy Uniswap on a layer 2 with like totally different code, even if I'm using the same, let's say, names for functions or something like that. And so I get like when you're calling a function on the layer 1, the code base is anyway there. So if you know what function you're calling, then you know what the opcodes are and so on. But if here the reference is to a function where the sort of code base is on layer 2, then how does the layer 1 know what the body of the function is?
Yes. So yeah, you're right. If you're using Uniswap on the rollup, you're using code that is stored in the rollup state. So the code is known to Ethereum in a way because when the code was deployed on the rollup, the function that deployed that code on the rollup had to be made available at some point on Ethereum. So Ethereum
This
at
is the
some
posting.
point,
This is the posting of activity from the rollup.
yes,
Okay.
yes. So the code was published and was committed to in the state of the rollup. So as I said previously, Ethereum doesn't need to keep this data around forever. So Ethereum doesn't need to be a full node or an archive node of the rollup. Whenever Uniswap is triggered, so let's say the code was deployed a year ago, Ethereum has long forgotten about the transaction that posted that rollup.
Wait, but sorry, can you clarify that too? When you said this thing about forgotten, it was also confusing to me at least, because ultimately whatever is being, the posted data is on a block on the Ethereum blockchain, right? So when you say forget, like, what do you mean? It's still there, right?
Yes. So today you're correct. The code that's posted on Ethereum as data is kept around forever because it's posted in a block and the blocks are currently kept around forever. There's actually an EIP, so one Ethereum like improvement proposal that argues that nodes don't need to keep the history of all the blocks forever. They only need to have this history available at some point, so this history to be available, but the history itself doesn't need to be kept forever because it can be recovered by having some finalized block that you can refer to and check that the history corresponds to that block. So that's one point. The other point is by decoupling the data posting from the blocks with this EIP 4844, there are special rules for the transactions that are posted as data on Ethereum. So these containers that are posted in 4844, these can be forgotten after some time, which means that the full node of Ethereum will eventually just remove the container of data from its server after, I think, 2 weeks was the measure.
Okay, but then to clarify, the reason that the sort of function call is sufficient for Ethereum to understand what needs to be executed is that the previous publishing of sort of the contract creation on the layer 2 to the layer 1 is there somewhere. And so that's how,
yes.
So for example, when you have these optimistic rollups and you go through these challenges, this is sort of where I was thinking, like, so then you would need to know kind of what exactly the code is. And this is how they know it's because of the publishing to the blockchain from the initial contract creation to the layer 1.
So,
okay.
Yes, correct. So if you run a full node of the rollup, you will have the entire state of the rollup at your disposal, including all the code of all the contracts that were deployed on the rollup during its existence. So as a full node, you're able to process transactions, actually execute them, not just read the data of the function call, but actually execute them against your local state and prove to yourself that you're moving the state forward correctly, given the state that you already have.
But so then,
So
I just at a high level, then would you say it's reasonable to say that one of the big advantages here from the rollups is that you don't have the sort of redundancy of execution that you have on the layer 1? So like even if this stuff is a lot of data, etc., at least when it's sort of operating on the layer 2, it's not multiple nodes executing it, and it's not multiple nodes storing it even, right? Or certainly not
Correct.
thousands of nodes. Okay.
Yes, yes. It can be a few super fast nodes that have very large hardware requirements, for instance.
Yeah.
Yeah, I think a few is important. So this idea of like the operators need to rotate. And if you want to be an operator, you will need to have a full node of a rollup. So yeah, you can significantly increase the resource requirements, which will of course decrease the number of full nodes that you have for the rollup, but it won't decrease its security as long as proofs are communicated to the layer one. Yeah, and this is how you get the scaling improvements of the rollup.
Okay.
Thank you, Paul.
Yeah,
All right, I think that's a good place to end, because I got to run. Although I feel like normal, I wish I had like another 5 hours to sit and grill Barnabé on like what's going on, because I find it super interesting.
Next month.
But yeah, so thanks a lot for coming to give the talk, and we'll end the stream here.
Thank you, Matt. Thank you, Fahad.